Okay, so today's video is going to be looking at collision theory. So giving a bit of a recap about what is involved for collision theory, what do we need for it to happen, and using some examples to demonstrate this definition. So to begin with, the idea is that collision theory is relating to chemical reactions. So we say chemical reactions occur in everyday life. It could be that we have some sort of reactant A reacting with reactant B to produce C. You could have A plus B going to make two products. You could even have just one reactant breaking into two different products. But in every situation, what has happened is some sort of rearrangement of atoms. And so with that rearrangement of atoms, you've gotten some sort of chemical change occurring. Now, in order to explain how those chemical reactions occurred, scientists came up with this idea of the collision theory, because there are some reactions where they do happen quite easily. They'll just occur without much help being needed, whereas some reactions require more help being needed. But scientists boiled it all down to the idea that we need this collision theory to explain why these chemical reactions occur. So if we have a look at that collision theory, the essential element of it is that atoms or molecules or compounds are going to collide in order to react. So that first thing is that they must collide in order to get a chemical reaction. So say you've got your molecule A, you've got your molecule B, they're going to collide together, and then some sort of chemical reaction has occurred to make an AB connected together, or some sort of new compound C. But the idea is that they must have collided in order for that reaction to occur. Now, when they do collide, however, a few different things can happen. They could actually collide and no reaction might occur. It all depends on the situation and how they collided. And so that brings us to not just the fact that they must collide, but they must follow a set of rules. Now, the very first rule for that is that they have to collide with the right amount of energy. And so we call that the activation energy. So if we have some sort of chemical, it usually starts off at a certain amount of energy, and this is just over time, and this level of energy tells you how much energy that molecule or stored potential chemical energy that model has. But in order for it to react, it needs to gain a certain amount of energy, and when it will react, it might release energy and come down to a lower state. So it could be that this is AB, and when it reacts, it's going to make A plus B as its products. But the idea is that there's a bit of a difference between what it started off as and what it ended up being. And so we refer to this as the activation energy, or EA. So that activation energy tells us how much energy did it need in order to collide. Now, if this AB was to collide without the right amount or without enough activation energy, it would not result in a chemical reaction occurring. This is an example of an exothermic reaction, whereas we've also got the other end of the spectrum where we start off with something that's a bit lower and then we gain a large amount of energy in order to bring it higher. And so this is an example of an endothermic reaction, so still energy over time, but it might be that this one is A plus B making AB. And this time, our activation energy is much greater because we need to gain a much larger amount of energy in order to allow that chemical reaction to occur. And so in both instances, when those particles are colliding, or whatever the compounds are that are colliding, they need to collide with the right amount of energy, otherwise that reaction would not occur. If they collide with the right amount, then it will occur, and we've got what's called a successful collision. And so this is what we're aiming for, this successful collision, because this is what will help our chemical reaction to occur, and also hopefully make it occur at a faster rate. However, it's not just needing enough energy to collide with, we also need to be in the correct orientation. So if we go to our list, so these are requirements for a chemical reaction to occur. So we said that they must collide, that they must collide with the right amount or enough energy, or they need to collide in the correct orientation. So what this means is that they need to be at the right angle. Now this seems a bit weird since we're talking about atoms, but when we look at the orientation of those different atoms, say you've got something that has, let's just say, hydrochloric acid. So we've got a H, we've got a Cl, and that's going to react with magnesium, so Mg. So this reaction, normally we say that magnesium reacts with hydrochloric acid to form magnesium chloride plus H2 gas. So in this instance, this magnesium and this chlorine want to join together. Now, how I have them orientated at the moment, if they were to collide as they are, the magnesium and the hydrogen are knocked together, and what's going to happen is you are not going to get a reaction occurring, or you're going to get an unsuccessful collision. However, if we then orientate them a little bit differently, so changing the orientation of the page, and have our magnesium there, and this time we're going to have our chlorine on the outside, and then our hydrogen, and now when they go to collide together, this magnesium and this chlorine are now in the right orientation that they can now collide to try and make, oh sorry, I did make a mistake, this was meant to be MgCl2, and if I balance this out, don't worry about the balancing at the moment. The main idea is that magnesium and chlorine want to be connected together, so they would need to be orientated to connect, so that when they do collide, we're now going to be able to get our MgCl2. Now, it's a little bit more complicated to make that Cl2, considering that we've got one hydrochloric molecule and one part of magnesium. It doesn't really matter too much about explaining how this MgCl2 forms altogether. It's a multi-step process. It's a little bit more complicated, but the main thing is that they need to be orientated in the right direction in order for this reaction to occur. Another example of this is looking at the reaction of NO2 with ozone to make, NO with ozone to make NO2 plus oxygen gas. And in this instance, we've got nitrogen, we've got an oxygen, and then this one is actually 3 lots of oxygen. And when they react, that oxygen needs to be able to react with that nitrogen in order to produce a nitrogen with 2 oxygens attached, and then that O2 left over. So without that happening, if this was to go and attack instead, or collide with the oxygen, colliding with the oxygen, we would get an unsuccessful collision occurring. And so that is the whole basis behind our collision theory. The idea that the particles must collide, but they must collide with the right amount of energy and in the correct orientation. Now, what we're going to be looking at in class is how do we manipulate that idea? How do we manipulate getting enough successful collisions for this reaction to occur, or to occur more at a faster rate? And the idea is that if we know that we need to get them colliding, we can try and increase the amount of collision. And if we increase the amount of collisions that are occurring, there's a greater chance that we're going to get those successful collisions occurring, because more chance that they're going to be colliding in the right orientation. But also what we can do is we can manipulate this energy, so by providing more energy. And so if we provide the particles with more energy, not only are they going to have chances to collide, but when they do collide, they're going to have more energy when they collide, so there's a greater chance that they're going to collide with the right amount of energy or more energy, which will also give us a successful collision. Because if we have a look at what a theoretical scenario, so particles really, they go in all directions. They just move around randomly. They aren't really thinking about where they're going because they can't think. But the idea is that in a certain amount of space, they're going to move around and they might collide. They might not. But according to our collision theory, hopefully they're going to collide with the right amount of energy and and the correct orientation in order for that reaction to occur. So there's a few things we can do to increase the amount of collisions that can occur, and that is things like increasing the concentration or the surface area, and also for gases, increasing the pressure. So we'll talk more about that in class in terms of how this last one works. But the idea is if we do all that, we're going to increase the chances of the particles colliding with each other. And we want to word it as successful collisions. So we're increasing the chances for successful collisions occurring. Because the greater number of successful collisions you've got occurring, the greater chance that this chemical reaction will increase, or the amount of reactions that occur will increase. The other thing we can do, though, is we can increase the amount of energy that we provide to them. So if we're increasing the amount of energy we provide to them, what we can do is we can increase their energy by increasing the temperature. So this provides them with more kinetic energy because they'll move around faster. And so if we're supplying more kinetic energy, each of these particles is actually going to have more energy for when they collide, and so they might collide faster. And also if they're moving faster, then we're also actually going to increase the chances that they have to collide. But the main thing for temperature is that kinetic energy. And the other thing we can do, depending on what type of reaction we have, is light intensity. So if we provide them with more light, we're providing them with more thermal energy depending on the reaction, and that can also increase the amount of energy they have. The last one that we can do to manipulate that is also using a catalyst. And a catalyst is important because then we're going to lower the amount of energy they needed in the first place. So it lowers the activation energy needed. And if we lower the activation energy needed, then there's a greater chance that they're going to have the right amount of energy. Just E for energy. And so in this case, let me just separate this out. These factors, so concentration, surface area, pressure, temperature, light intensity, and a catalyst, we can use all these to manipulate the collision theory and what we know about how to get successful collisions in order to try and increase the rate at which these particles are going to collide to increase a reaction. Okay, so that is just a really short recap of collision theory. The main thing that we're looking at again is that when we have a chemical reaction, we must have the particles colliding in order to get a successful collision, or in order to get a chemical reaction to occur. They need to react with the right amount of energy and in the correct orientation in order for that chemical reaction to occur. But also we can manipulate that by increasing the concentration of our reactants, increasing the surface area that they're exposed to. If they're gases, so it only works for gases, we can increase the pressure of the reacting vessel, and then we can also increase the temperature, light intensity, or add a catalyst in order to make the reaction go faster, or at a bigger rate. Okay, thank you for watching, and we'll talk more about how each of these things affect rate of reaction in class in more detail.